Okay, we're recording, we're live. Okay, all right. So here we go. Okay, back to water hammer phenomenon. Okay, so I think where we ended off in the last lecture, we talked about water hammer effects. All right. What do you mean by water hammer effects? The formation of the pressure wave that travel upstream and then downstream again, and then upstream and then downstream again. So we have inspected the pressure variations as well as the velocity variations, as well as the change in the flow direction in quite a fair bit of details in our last lecture. And I believe we have covered, the pressure variations experienced by the valve as the water hammer effects, right? Gets itself sorted out, conducting upstream, propagating upstream, downstream, and upstream, and so on and so forth. Right? So we have seen the pressure variation, the PET diagram. Okay. Now the thing is, okay, the question has always, I mean, there's an outstanding question, isn't it? If you think about it, okay. Because so far, all right, we've been looking at water hammer effects, okay, when the valve is closed very, very rapidly, okay. But what happens to the water hammer effect if, let's say, the valve, right, is not closed that rapidly? All right, let's say, instead of shutting off the valve in half a second, I take my own sweet time and close the valve, right? Okay, let's say, using 2 seconds or even 3 seconds and things like that. Okay, so in this case, all right, well, what we're going to do for water hammer effects, all right, over here today, is to compare, all right, the differences between what we call a rapid valve closure and a slow valve closure. Okay, all right, what will happen to the water hammer pressure, whether it's going to be that high or it's going to be much lower, and so on and so forth. Okay, so over here we define rapid closure, all right, as the situation when the valve is fully closed before the pressure wave that's produced at the valve when you shut off the valve suddenly, okay, propagates back to the reservoir and travel back to the valve again. Okay, so rapid closure basically means that you have to shut the valve so fast that the pressure wave, right? Okay, by the time the pressure wave travels back to the valve, okay, the valve is already fully closed. Now, slow closure, I think I made a mistake here. I put close closure. Okay, can you please correct it to slow, please? Okay, I noticed it when I went through this lecture slides last time. Okay, this should be slow closure. Now, what is slow closure? Now, slow closure is the other way around. So what happens is slow closure simply means the situation where the valve is only fully closed, okay, after the pressure wave has hit the valve. All right, that means when the pressure wave has propagated upstream and then back again, the valve is not fully closed. Okay, and I think that intuitively, all right, means that there will be some pressure relaxation and probably the water hammer pressure will not be that high if you think about it. Because if the valve is not closed, that means the pressure wave, all right, will have means to propagate further downstream and basically relaxes the pressure buildup. Okay, now, if you guys recall this, this came from the earlier slide. Okay, if let's say we were to plot the pressure variation versus time, okay, of the pressure level that's experienced by the valve, okay, and what happened is at time t equals 0, that's where the valve gets shut off, okay, and for rapid closure, this is what happens, right? The pressure, all right, the original pressure P0 is going to increase drastically up to a maximum pressure, and that will be the water hammer pressure, and as the water hammer travels upstream and downstream again, the pressure experienced by the valve will be maintained at this level. Okay, now the time taken for the pressure wave to travel upstream and downstream will take a total time span of 2L divided by C. Okay, I suppose this is quite logical because you know why? Let's say the upstream distance is L. Okay, the time taken for the pressure wave to travel all the way upstream from the valve location, all right, that means travel throughout the entire pipe length until it hits the reservoir, is nothing but the length of the pipe divided by the speed of the pressure wave. That's going to give us the time, isn't it? But remember, it has got to travel. We're interested in traveling, in the pressure wave, traveling back to the valve again. So basically, that means it's 2 times L over C. So this is the reason why over here, the pressure increment over here, okay, stays for a duration of 2L over C before it drops again, before it drops drastically as the pressure wave travel upstream again, okay? So let's define a pressure wave reflection time, TR, as 2L over C. That means it's the time taken for the pressure wave to be reflected back to the valve, okay? And by definition, okay, if the closure time, TC, is less than TR, okay, that means the valve is shut off before, or it's fully shut off before the pressure wave actually comes back to the valve again. All right, we'll call it a rapid closure. Now, if the closure time, TC, is greater than TR, okay, meaning the valve is not fully closed by the time the pressure wave actually comes back to the valve again, we'll call it a slow closure. So this is by definition, okay? Now, like I said earlier on, okay, logically speaking, try to imagine your mind, right? If, let's say, the pressure wave, okay, by the time you travel back to the valve and discovers that the valve is only like sort of like half open, that means the pressure wave can continue to so-called seep through, all right, propagate through the whatever opening that the valve still have. Intuitively, the pressure that is going to be experienced by the valve is probably not going to be as high as the one that's experienced for a rapid closure, which is the maximum water hammer pressure there. So the water hammer pressure, okay, for a slow closure scenario will be less severe and will be lower than the maximum water hammer pressure, all right, okay, for a rapid closure, okay. And now it can be defined, okay, that the water hammer pressure, okay, pH prime, experienced by a slow closure is nothing but TR divided by TC. So the reflection time divided by the closure time multiplied by the maximum water hammer pressure for a rapid closure. Okay, now this is a linear relationship. Okay, is something that is not that fantastically accurate, but it's a good enough approximation for something that's highly empirical. Okay, as you've seen in the video, okay, I believe last week, I've seen that, you know, what happened was that once you shut off the valve rapidly and a water hammer phenomenon actually manifests, what's going to happen is you're going to have, you know, the pressure sometimes falling below the vapor pressure. There can be like bubbles and gas pockets and things like that. So it's very, very non-linear, okay? And it's very, very difficult to nail down precisely the time, okay? Sorry, not the time, the pressure, the water hammer pressure, if let's say the valve is closing very, very slowly, okay? But for empirical flow behavior such as this, all right, an estimate, right, based on the linear relationship, right, is often good enough, or at least it gives us, you know, at least the order of magnitude, okay? But probably a lot better than that, right? Quite close. Okay, now just to illustrate the principles, the differences between rapid closure and close closure, and slow closure influence upon the water hammer effect. All right, let's take a look at a very simple example. Okay, now we have a potable water pipe. We're told that this water pipe has got a length of 600 meters and a diameter of 1.2 meters. Okay, so what happened one day was that a valve at the end of the pipe, okay, is used to stop the flow for maintenance purposes. Okay, assuming that the pressure wave velocity C is 960 meters per second, and the water flow rate is actually originally 0.9 meter cube per second before you shut off the valve. Determine the maximum water hammer pressure at the valve, or experience at the valve there. Okay, if let's say the valve is closed instantaneously. Now, if the valve is closed instantaneously, surely there's a rapid closure. Okay, all right. But we're also asked to determine the maximum water hammer pressure right at the valve if let's say the valve is closed in 4 seconds time. Now, 4 seconds time, I mean, it's a bit hard to decide, right? Is this a rapid closure or is it a slow closure? Okay, this is something that we have to ascertain when we try to solve the problem. Okay, so that's for part A. Now for part B, we're asked to find out the maximum water hammer pressure if let's say the valve is adjusted so that the flow rate reduces almost instantaneously. Now this means rapid closure from 0.9 meter cube per second, not to 0, but to 0.3 meter cube per second. And this 0.3 meter cube per second, all right, was maintained. All right, okay, it doesn't go further to 0. Okay, so we have a few different scenarios over here. Okay, so we're asked to find, estimate the water hammer pressure at the valve. Okay, now for part A, part 1. Okay, now if the valve, as I mentioned, if the valve is closed instantaneously, so surely, all right, we're going to get the maximum water pressure, water hammer pressure. Now, to get the absolute maximum water hammer pressure, we can make use of this very simple formula whereby water hammer pressure, pH, is nothing but the product of the fluid density, which is rho, the pressure wave velocity, which is C, and the differences in the velocity, okay, between the initial velocity and the final velocity. Okay, now if the valve is closed instantaneously, if it's closed means that the final velocity surely must be zero. So if the final velocity is zero, this formula, all right, can be further simplified to this. pH is nothing but rho CV, where V will be the velocity associated with the original flow rate. We know that for water, we can assume rho to be 1,000 kg per meter cube. C is given as 960 meters per second. As for velocity V, I'm quite sure you guys know how to calculate from the flow rate and cross-sectional area of the water pipe. If you think about it, we are given the diameter. Okay, so it should be quite straightforward enough for you guys to know how to calculate the velocity. Okay, so once I come up with this relationship, okay, all right, punching these numbers in the calculators, you're going to get a maximum water hammer pressure of 764 kilopascal. So this is the highest water hammer pressure that one can get from this particular scenario, because if you think about it, this is the water hammer pressure that's associated with rapid closure of the valve. Okay. Now, what happens when the valve is closed actually in 4 seconds time? Okay. So first thing first, all right, how do we know it's a rapid closure or a slow closure? Okay. What we can do is, okay, to firstly calculate the reflection time and then basically, all right, compare the 4 seconds with the reflection time. Because the reflection time is going to tell us how fast, okay, or should I say how long the pressure wave takes to propagate upstream and then gets reflected at the inlet and then propagate downstream again before hitting the valve, okay? Now the reflection time, the pressure wave reflection time, TR, again, like I said, is defined as 2L over C. Okay, we know what's L. Okay, 600 meter long. Okay, plug in your 600 meter here. What's our C? Our C is 960 meters per second. That's the pressure wave velocity. Okay, I'm quite sure you guys can work out that TR is 1.25 seconds. Okay, all right. Now, if the reflection time is 1.25 seconds, okay, and the closure time, all right, that means the time taken for the valve to be fully closed is actually 4 seconds. That means the pressure wave, all right, has already come back to the valve before the valve is actually fully closed. Okay, so surely this particular scenario will be one that's associated with a slow closure. So we can make use of this empirical formula, okay, to allow us to calculate, right, the maximum water hammer pressure for this particular slow closure scenario. All right, so TR divided by TC multiplied by the maximum water hammer pressure for a rapid closure, which is something that we found out, isn't it? 764 kilopascal. TR, we managed to find out is 1.25 seconds. TC, all right, the closure time is 4 seconds. Okay, so I'm quite sure you guys know how to work this out using our calculators. And in this case, the water hammer pressure, all right, for this slow closure scenario is 236 kilopascal. So as you can see, 236 kilopascal is quite a bit smaller, all right, than the maximum water hammer pressure, all right, associated with a rapid closure. Okay, all right. So this is how we make use of the relationship that we've gone through so far. Okay. Now how about part B? Okay, whereby the valve does not close, all right, 100% at the end of the day, but rather the valve, all right, basically just, all right, restricts the flow, all right, to a smaller flow rate. That's all, and then it holds it there. Okay. Now for us to calculate the water hammer pressure, once again, that means we have to invoke this fundamental formula. Except that in this case, V2, all right, which is the final velocity, is not going to go to zero. Okay, but V2 will be the velocity that's associated with this 0.3 meter cube per second final flow rate. Okay, I think I made a mistake in explaining in some of the words here. All right, so can you please correct this? Okay, so V2 is not zero, but rather the velocity associated with 0.3 meter cube per second. Okay, I think I put in some words which are quite confusing. I'm not too sure what happened. All right, so this should be the one. Okay, so if that's the case, all right, surely we'll be able to work out V2 based on 0.3 meter cube per second, isn't it? As for the original velocity, I'm quite sure we know how to work it out as well. In fact, we can just use the velocity that we worked out previously. But in this case, I prefer to work from scratch. And if you think about it, density rho is 1000 kg per meter cube here. All right, CP, well, it's actually C. All right, okay. All right, it's basically C of pressure. Well, it's 960 meters per second. Okay, V minus V2. All right, original velocity, initial velocity minus final velocity is nothing but, if you think about it, the initial flow rate minus the final flow rate divided by the cross-sectional area of the pipe. Okay, and you can work out that the water hammer pressure in this case, okay, it's actually 509 kilopascal. Now, some of you, all right, may wonder, why is this pressure so high as compared to, all right, to the slow closure? All right, okay, even though, all right, the final flow rate is not zero. It seems strange, isn't it? Why is it still so high? Okay, all right, the reason is that, okay, just because there is a non-zero but final velocity, okay, doesn't take away the water hammer effects if the closure, or in this case, this partial closure, still take place in a rapid manner. Okay, it's the speed at which you adjust your valve that matters more. Okay, when it comes down to the water hammer effect. Okay, all right. So this is something that I think I have to reinforce that. Okay, so that's the reason why, right? Even though we do have powerful valves that can shut off the pipeline, right, the flow within the pipeline very fast, we try not to do that because that may, you know, in a worst case scenario, all right, gaskets and bolts and nuts may get blown out. Okay, worst case scenario, the pipes may rupture, and I believe this is not something that, you know, you want to see. Now, if it happens in your washroom, right, fine, you know, you get a burst pipe. I'm quite sure you guys can find a valve to just shut it off and call the plumber. Okay, but if you think about it, if let's say you try to do this in an industrial facility, let's say an oil refinery, and you know, let's say despite your colleagues' advice and warning, okay, you try to shut off the valve rather rapidly, okay, you may get yourself into quite a bit of trouble, okay, when it comes down to the integrity of the facility. Thankfully, modern technologies, modern systems have got fail-safe that prevents, that basically, right, pre-program the valve to close in a rather slow manner, especially when the flow rate is very, very high. So it depends. Right? For some pipelines, whereby the flow rate is not too high, well, it doesn't quite matter. But if I'm talking about 14-inch 40-inch metal pipes that carries crude oil or processed oil, okay, or any other fluid, okay, chances are, all right, you don't want to shut off your valve way too fast, okay, you don't want oil to spill all over, or there'll be a catastrophe, all right, so yeah, all right, just have to watch out for that. When it comes out to applying this to the real world scenario. And of course, I want you guys to appreciate the implications of a rapid closure and slow closure by running through these numbers, these examples, and let you see the numbers for yourself. Okay, and that's all we have got for water hammer effects. Okay, the last topic for this chapter will be one that's associated with surge control. Now, what is surge control? Surge control essentially means, you know, whatever physical ways, all right, that we can impose upon the flow delivery line or the pipeline, such that we are able to mitigate any sudden increases in pressure, such as the one that we saw in the water hammer. All right, topic. Okay, as you guys can see, right, the pressure actually just goes up, right, 700-800 kilopascal, and things could be worse, a lot worse, if let's say the velocities differences are really huge. Okay. So what happened is, okay, this is what surge control is about, is to mitigate all this sudden increase in fluid pressure, okay, be it associated with rapid valve closure or be it associated with any other non-intentional things happening. You will never know, right? Okay. So what happened is, okay, this is actually very, very important in modern flow facilities. Such, again, I want to use oil refinery. Right? Sometimes you see those vertical, sometimes you see vertical tanks. All right, sort of like standing vertically, you know, in the middle of pipelines. So those are surge tanks. It may or may not be vertical. Some surge tanks are actually horizontal. It depends on, all right, the applications at the end of the day. Okay, And ultimately, surge control is a very, very useful way and very, very important way of mitigating possible physical damages to the facilities. I mean, you have to, okay, because there are safety regulations that govern all these high pressure facilities, especially if you think about it. If I talk about oil refineries, safety standards has got to be quite high. You don't want something bad to happen, and next thing you know, you have a fire on your hand. Okay, all right. So this is what surge control is about. I like to use a very funny example. Okay, I'm quite sure you guys love persevering, or at least I do. Okay, so imagine, right? I'm quite sure, right? You have this bloody kaiju right, fighting with the Jaegers, yeah. All right, and imagine the bloody kaiju says that, feels like, I'm feeling a bit tired, I need an energy boost. Okay, so of course this is entirely fictional, huh? Okay, I cough out this scenario by myself. Please don't quote me, yeah. All right, I'm not too sure whether I don't want to see this appearing in the next Pacific Rim movie, yeah. So imagine this Jaeger say, "Oh, I need to bloody recharge." Ah, bloody hell, there's a hydroelectric dam, yeah. Okay, that's my USB 3 cable, my Thunderbolt cable, and things like that. I need to charge myself up. All right, and imagine we say that, no way, Jose, right? No way, I'm going to get a single drop of electricity. I'm going to shut off the valve like right away. But if you think about it, okay, all right, you're talking about massive amount of flow rate of water running through the turbines, running through the tunnels and things like that. You can't just shut it down just like that, all right, without causing physical damage. And physical damage is very, very real when it comes down to hydroelectric dam, isn't it? So we have to think of something else, right? We have to make sure that, hang on, are there ways that we can build into the facility right in the first place? Okay, all right. So that at the end of the day, should we need to go for rapid closure, all right, the facility will not be damaged, or else we'll be angry. This guy will be, well, will be rather miffy, isn't it? Okay, all right. So yeah, okay. So this is what surge control is all about. Okay, so what happened is, all right, surge control involves the use of surge tanks or surge chambers. Okay, there are many types of surge control devices out there. Generally speaking, all right, okay, they look like tanks or chambers. Okay, and all right, if you guys are interested, you guys can actually go and Google all these surge control stuff, devices. Okay, but I'm going to just talk about the general surge tanks and surge chamber, which is the basis of more advanced types, if you think about it. Now, the simplest surge tank, if you think about it, is a very, very simple vertical tube with an open end, right? As you guys can see in the figure here. So imagine we have got this reservoir, okay? And what happens is when the valve is open, water is flowing from the reservoir through the pipe, and the water will be, flowing downstream happily, right? And what happened is, okay, all right, there'll be a certain water level here within the surge tank. In this case, this is what we call an open top surge tank, whereby the water here within the surge tank is exposed to atmospheric pressure. Okay, and there'll be a height difference between the reservoir surface height versus the height of the water. All right, that's within this open top surge tank. I'm just using water for the sake of simplicity. Okay, now, so this is where, everything is operating normally, right? You allow water to flow out from the reservoir to go somewhere, all right, to do its thing. And then you have got this open top surge tank right in front of the valve. Okay, in fact, the surge tank must always be between the reservoir and the valve. Otherwise, it doesn't make sense to put this surge tank, all right, after the valve. Because if you think about it, it doesn't make sense. All right, when you close the valve suddenly, what's going to happen is water hammer pressure is going to be on this side, not on the other side. All right, so water hammer pressure is going to be observed on the upstream side, not the downstream side. So clearly, your surge tank has got to be on the upstream side. Okay, so let's say this is a normal operation, and then for some reason, all right, I have no idea why the animation doesn't work. Well, it worked, but what happened to the valve? Why is it punching through the pipe? Okay, anyway, assuming that the valve, because I think I switched the format from 69 to 4 to 3, something like that. Okay, so anyway, assuming that the valve does not punch through the pipeline. Okay, all right, this is what we get. Okay, all right, so all the flow will be stopped right at the valve, and there's no more flow after the valve. Okay, but as we all know, okay, the flow surely must have got its flow inertia, the flow momentum. All right, you cannot just stop it. Okay, what happened is, okay, the pressure built up here will cause the water level, all right, to surge into the surge tank such that the water level, all right, actually increases. All right, depending on how fast you shut off the valve, the water level change may or may not be very, very drastic. Okay, in this case, I show a rather drastic one. Okay, but the thing is, it's a dynamic thing. The water level doesn't just go up and stay there. All right, the water level. So immediately once you shut off the valve, bang, okay, the water will surge to the surge tank, goes up and hit a maximum level, let's say. Okay. Oh no. That's hilarious. Okay. Forget about the animation. Okay. Okay. So the water level is going to go up, hit a maximum level. All right. And because, like I said, right, the water surface is a dynamic one. So it's going to undergo oscillation, as you guys can imagine. Okay, because the pressure waves is actually traveling along the pipeline, up and down. All right, travel up and travel down. So surely, right, the variations in the pressure is going to cause the amount of water in the surge tank to vary. All right, gradually as the pressure wave gets damped up. Okay, so the water level, once it hits the maximum level, all right, it's going to go down, it's going to go up again, it's going to go down, and the delta Z, or in this case, let's say the Z will basically, all right, gets gradually reduced, all right, until all right, everything gets damped up. Why is this thing moving again? Oh no, that's hilarious. Okay, anyway, okay, so okay, so what I'm trying to say is, okay, so in short, once you shut off the valve rapidly, okay, the water will go into the surge tank. It'll, right, if it naturally goes up, hit the maximum level, comes down again, goes up, come down, goes up, come down after I don't know how many cycles, depending on the pressure, of course, and the amount of water in the surge tank and how to design the surge tank. Eventually, all right, okay, the water level within the surge tank will reach a final steady state level. Okay, now for open surge tank, if you think about it, both the reservoir and the open surge tank, they are both exposed to the atmospheric pressure. And with the valve closed, it means that at the end of the day, all right, the water level within these two devices, the reservoir and the surge tank, all right, will be at the same level. Okay, now things will be a little bit different if I'm talking about a closed surge tank or a pressurized surge tank. As the name implies, a closed surge tank means that instead of having an open top, you're going to have a closed top. Okay, and you're going to have a pocket of trapped air within this surge tank. Now, the good thing about having a closed surge tank is that if you can imagine, as the water level goes up and comes down, all right, the air gets compressed and decompressed. Okay, and this will sort of like dissipate the energy that the water in the surge tank may have, and the pressurized air, all right, acts to sort of like put a cap on the amount of water that can go into the surge tank because it's going to be pressurized. Because as the water goes up gradually in the surge tank, all right, the pressure of the air that's trapped inside the surge tank is going to go up. And if the pressure goes up, the air pressure goes up, it's going to be pushing down the water as well. So it's a rather nice way of controlling the amount of water that you allow to go into the surge tank. Okay. And what happened is, oh no, oh no. Okay, I better don't do animation next time. Okay. Okay, but the difference, okay, the most interesting difference between a closed surge tank and an open surge tank is because of this trap air pocket here within the closed surge tank is that the water level of the reservoir will not be the same as the final water level, all right, of the water inside the surge tank. Okay, all right. It looks like I need to get rid of all these moving parts. Okay, so that's the only difference. Okay, now I must preface by saying that solving problems associated with a closed surge tank is a lot harder than to solve a problem that's associated with an open surge tank because we have to consider the pressure variations of the trapped air here. Okay, so I don't think it will be wise for us to look at a closed surge tank per se. Okay, all right. Now, one of the most important fluid flow problems, all right, if you're talking about surge control, all right, is to predict the maximum level, all right, that the water will reach within the surge tank. Okay, because if you think about it, you have no idea how high the water level is going to go in the surge tank. You may end up with a surge tank that's way too tall. All right. So imagine, right? Let's say, all right, in reality, let's say, okay, the water level increase, all right, it's probably, let's say, 2 meters, but you're going to build a 10-meter silo. All right, that doesn't make sense because, okay, firstly, it's going to be expensive. Secondly, all right, it's going to be taking up more space. And thirdly, probably it looks way uglier than a shorter surge tank. Okay. Conversely speaking, if let's say you underestimate, the water level increment in the surge tank, things become actually quite dangerous, isn't it? Because what's going to happen? Imagine you have a open-ended surge tank. Water is going to come spilling out from the surge tank, isn't it? Okay, all right. Maybe for less critical industries that may not be a problem, but it's always not that entirely satisfying. All right, even if let's say you don't mind water spilling out from the surge tank, okay, because who knows what kind of dangers it may pose. Okay, so now how do we analyze such controls, such tanks in an analytical manner? Okay, based on whatever equations we've learned from the unsteady flow chapter so far. Okay, Bernoulli's equation again. All right, energy balance equation, all right, based on the Bernoulli's equation. So I'm quite sure you guys have seen this equation, are quite well versed with it. And basically, again, this is an energy statement equation that basically says that the total sum of three flow energy components, which is the static energy pressure head, static pressure head, kinematic pressure head, and the gravitational pressure head, the summation of these three terms at somewhere that's far, let's say at the reservoir, surely must be the same as the sum of the same three energy terms, but taken at another location, all right, plus whatever frictional flow frictional losses that you're going to encounter along the pipeline, plus whatever minor losses, and so on and so forth. Okay, and of course, if let's say your pipeline has got a pump somewhere, I'm quite sure you know where to put the pump pressure here. Okay, now if you were to simplify this based on a typical surge control scenario, such as this, okay, you realize that this equation can be simplified to this. Okay, whereby we have Z naught, I'll talk about Z naught later, whereby we have Z naught equals to V naught squared divided by 2G. V naught will be the initial velocity before the valve has been closed, plus F into L over D, V naught squared divided by 2G, plus, of course, the summation of the minor losses. All right. Now, what is V naught? What is Z naught? Z naught, all right, is nothing but the water level, okay, in the surge tank. The height of the water level in the surge tank. Okay, hang on. What's everything going to reverse? Okay, this will be Z naught. Okay, all right. Jeez, this is so strange. All right, I do apologize for that. Okay, now you can actually simplify this. Okay, further, because I'm quite sure you guys noticed that all of this has got a common term, and that is V naught squared divided by 2G. All right, so if you take out V naught squared divided by 2G out from these three terms, and then consolidate their coefficients, right? We can actually express Z naught as capital letter K, right? Cap K into V naught squared divided by 2G. And in this case, cap K will be 1 plus F over D plus summation of K. And this is only applicable for the scenario that we've seen earlier. If let's say the scenario changes here and there, let's say you have got two pipes instead of one pipe, and the two pipes has got different diameters, then you have to modify this equation accordingly. Okay. So what happened is, based on this equation, this rather simple equation, okay, all right, it can be seen that Z naught is a function of the velocity head, which is this, pipe frictional losses, and of course minor losses. I'm quite sure this is something that's intuitive, right, just by looking at that. Okay, now by right, okay, right, there's a full set of derivations that is probably going to stretch on for like 3 pages, 3 slides or 4 slides, okay, as to how we get this. But like I said, what do I always say? I don't care too much about derivations, okay? And I think that the derivation is going to be taking us way too long. Plus, it's going to confuse a lot more people, okay? So I make a decision, all right, to jump straight to the most useful expression that we can have for such control, okay? And I think this is better because I want to focus on your ability to apply this in real world scenarios, or at least for theoretical questions, okay, rather than going through the derivations, okay. So without going through all the detailed derivations, okay, save ourselves some grief along the process, okay, we do have this expression that relates the maximum water height level, Zmax, okay, to the other flow parameters. What is Zmax? So let's go back. Zmax will be this, okay? The maximum water pressure, the maximum water level in the surge tank upon a rapid closure of the valve. As you can see, it will have to be the first surge. Well, it can't be the second surge or the third surge because you know why? Because the pressure waves is going to get weaker and weaker, all right, as it travels up the pipe and come down the pipe, up the pipe again and down the pipe again, and so on and so forth. All right, okay. So if you think about it, the pressure wave will be the strongest, okay, in the very first instant. All right. So Zmax, okay, will be the maximum height, water height in the surge tank associated with the first pressure wave, if you think about it. Okay. So with that out of the way, and of course with the strange behaving valves out of the way, okay, this is what we have. Take a close look at this expression. On the left-hand side, we have 1 minus K AS. K will be this K. Okay, this is nothing too difficult. Okay, so that's fine. What is AS? AS is actually the cross-sectional area of such tank. Okay, divided by LA. L will be the distance. Okay, basically it depends on the location of the such tank. Okay, that's a query. Is Z not the steady state height? Z naught is the steady state height, yes. Z max is not the same as Z naught. I tell you what, you guys, later on when I go through the example, things will become clear. Okay, things will become clear because in fact, Z naught will be a negative number. Okay, let me just go through the implications of this expression first. Okay, so L will depend on the location of the surge tank. Okay, along the pipeline. A, or in this case, not AS, A will be the cross-sectional area of the pipeline. So long, right, you know the diameter of the pipe, okay, or the radius of pipe, you should be able to work out A. Okay. Now this fraction here, KAS divided by RA, or should I say this coefficient here, all right, will be multiplied by Zmax. Okay, the maximum water height achievable, all right, due to the first surge. So this will be on the left-hand side. On the right-hand side, we have an exponential, all right, of the product here. All right, the first term here is actually the same as the coefficient here. I'm quite sure you guys can see, minus KAS divided by LA. The second term here, all right, we have got K. Well, K is the same K as here. V naught square. So this is the initial velocity. So for us to predict the maximum water height due to the surge, okay, we have to know the initial flow rate, initial flow velocity, V naught. Because over here we need to take V naught, square it, and divide by 2G plus Z max. Hang on, I'm quite sure you guys must be surprised. Why is there no Z max here? Why is Z max not all the way to the left-hand side? Okay, and I'm quite sure you guys know what this entails. It seems to imply to solve for Z max, right, involve a trial and error process, don't you think? Okay, it's like comparing the left-hand side, comparing the right-hand side, and so on and so forth. Okay. Now, thankfully, or should I say, before I go to the thankfully part, okay, it can be seen from this expression that Z max, AS, and K cannot be solved explicitly, meaning they cannot be solved directly because all these are functions of the surge tank size. Okay, so the only way to solve this, or should I say the best way for us to solve this at this point, okay, based on what we know, is basically, all right, use trial and error. Okay, and the first step is to minimize the right-hand side, all right, value of this equation. And how do we minimize the value of the right-hand side? Is to basically, all right, set Z max, okay, all right, to be LA divided by KAS. Why do we do that? Why do we do that? Think about it. We want to do that because you know what? What's the minimum value that I can have? All right, to balance both sides. It's going to be 0. All right, things will be minimum. Let's say we can set the left-hand side, all right, to a net 0 value. And how do we get 0? It's going to be 1 minus 1. How to get 1 minus 1? That means I have to set Z max as the reciprocal of KAS divided by LA. All right, which means that Z max, all right, you can take the first approximation as LA divided by KAS. Okay, so I know this sounds a bit confusing and things like that. Let's take a look at the example. Things will become a lot clearer, including those people who ask questions on the chat box. Yeah. Okay. Okay, let's say we have a 90 cm diameter, 1,000 meter long pipe, steel pipe with a friction coefficient or friction factor of 0.015. All right, so it's shown schematically here. So this is the pipe. Okay, so this pipe actually supplies water from a reservoir to a small power station. Okay, at a rate of 3.2 meter cube per second. Okay, and what we have here is a 3 meter diameter. All right, open top surge tank. Okay, now this surge tank is actually located at 100 meters upstream of the valve. Okay, so now based on this information, so okay, maybe I should answer the questions. So Z naught, okay, all right, is the steady state height. So as you can see over here, Z naught is the steady state height. You know, the valve is fully open and things like that, steady state height. Okay, and it's in reference to the reservoir height. I believe this is our question. Okay. All right, so now this is the initial conditions, 0.9 meter diameter pipe, 1,000 length, worth of 1,000 meters worth of pipeline until from the reservoir to the valve, and the surge tank is 100 meters upstream of the valve. Okay, all right. So we're asked, okay, based on all this information, we're asked to determine the initial water height in the surge tank. That means Z naught. Okay, the steady state water height. Okay, when the valve is fully open. That's for A. For B, we're asked to find to basically estimate the maximum height of the surge in the surge tank. That means the very first surge, Z max, if the valve shuts off abruptly when emergency occurs. And to simplify problems, thankfully, well, this question tells us that all minor losses can be neglected. Okay, so this is the initial condition. All right. When the valve is shut off immediately, this is what's going to happen. Okay, since water can't flow through the pipe, through the valve now, because the valve is fully open, water will surge into the surge tank and basically reach a maximum height, Zmax. And Zmax is reference to the reservoir height as well. Okay, so now, since we know that based on this formula that we're going to use, okay, we have to find a whole host of stuff. For example, V naught. What's the initial velocity? And I believe we do have information to find out V naught quite easily. Okay, V naught is nothing but the initial flow rate divided by the cross-sectional area of the pipe. I'm quite sure this is something that's intuitive to you guys and something that you guys can work out rather easily. So V naught, all right, is about 5.03 meters per second. Okay, now for us to find Z naught, all right, since Z naught is a steady state thing, that means we just have to invoke the steady state Bernoulli's equation that we've seen earlier on, which is this. Where is it? Oh, I went too fast. Okay, hang on. This one. Okay, for this particular pipeline, because the scenario that we are looking at for the example is the same scenario for this one. Okay, so we can make use of the same Bernoulli's this energy equation. But of course, if let's say there's some changes to the pipeline, you know, to the flow system, then of course the equation may look different. Okay, now let's come back to this. Okay, but nevertheless, whatever energy equation that you use for the steady state condition, at the end of the day, your motivation is to first find out Z naught. Or in this case, because for part A, we're asked to find Z naught. Okay, so Z naught at the end of the day is simply a function of K times cap K times V naught squared divided by 2G, and cap K is nothing but the summation of the coefficients of these terms. Okay, but in this case, we are actually provided with all the information necessary to find out what's the product of F into L over D, and well, minor losses will be neglected. So I think at the end of the day, just make use of your V naught that you calculated from here, make use of information provided by the question, and solve for V naught based on the steady state energy equation. And in this case, Z naught is 20.6 meters, right, below the reservoir height. Okay, so that will go for part A. Now, part B will be the tricky one, okay, because part B is a question that's actually asking for us to find Zmax. Now, for us to find Zmax or to estimate for Zmax, we have to consider this rather daunting looking like expression. Okay, so first thing first, okay, all right, let's find out what's K. K is 1 plus FL over D plus, all right, summation of all the minor losses. Thankfully, this is all neglected. All right, so we can work out our cap K to be 16. Cross-sectional area of the pipe A can be worked out to be 0.636 meter cubed. Okay, AS, the cross-sectional area of the search tank, we're told that it's 3 meters, is it 3 meters diameter? Yes, 3 meters diameter. I'm quite sure you guys know how to calculate the area. Pi d squared divided by 4 is about 7.069 meters squared. What's V naught? V naught is something that we found out in part A, it's 5.03 meters per second. The length of the pipeline is 900. Aha! You guys might be wondering, why 900? Because the L here, all right, is actually, all right, the distance between the search tank and the reservoir. Think about it. Whatever pressure that's causing the water to go into the search tank, all right, is actually dependent upon the length of the pipe between the search tank and the reservoir. Correct? Unless you tell me that the reservoir is exactly at the same location as the valve. If not, all right, in this case, we know that the search tank is 100 meters away from the valve. So we have to take the 1,000 meters minus the 100 meters, okay, such that the L is 900 meters. Okay, once you have all these values, the way to solve this is you have to get a first estimate for Zmax. And Zmax, the first estimate, as we've seen earlier on, we can assume it to be LA divided by cap A, AS first. Okay, we worked out all these values. So plug it in. Zmax, the first estimate is 5.061 meters. Okay, now if you substitute Zmax into 5.061 meters, all right, you plug it in here, you plug it in there, all right, you try to work out the values of the left-hand side and the right-hand side and compare the values. At the end of the day, the trial and error should be such that you get same values for the left-hand side and the right-hand side. Okay, in this case, if you were to plug them in, okay, this is not exactly equal to 0 because there's some rounding off truncations and things like that. So the left-hand side is close to 0, but it's not exactly 0. It's minus 5.36 times 10 to the power minus 5. On the right-hand side is 0.006238. So I think it seems that we're lucky. The left-hand side is not really 0, but it's very close to 0. On the right-hand side is greater, it's a greater number, but it's not that great a number in absolute terms. It's still 0.006. Okay, now for practical purpose, this is close enough. But all right, if in the event, okay, they're going to get a far greater number on the right-hand side, okay, as compared to the value on the left-hand side, then you have to adjust the values of Zmax and try again. Let's, for example, the next second value that you try for Zmax could be 5.1, 5.2, 4.9, 4.8, and so on and so forth. So it's better that when you do all this trial and error, you have sort of like a table, right? Put them in tabulated manner. Okay, let's say the first column, all right, will be Z, value of Z. Second column will be LHS, the value of left-hand side. And then the third column will be RHS, value of right-hand side. And then as you try out different Z values, all right, so they can see the trends, the movements in the values of the right-hand side and the left-hand side and the right-hand side, and then adjust the trial and error values for Zmax, right, gradually. Okay, at the end of the day, once the difference becomes small enough, okay, that will be your so-called final Zmax. Okay, but for practical purpose intent, it's very often that this first estimate is good enough, because if you think about it, right, do engineers just take this value and design a pipe that is, let's say, 5.061 and take it as it is? No, right? When it comes down to engineering, we know that there are a lot of things that we can't really account for. And what happened is, okay, we're going to multiply this Zmax by, let's say, a safety factor, let's say 2 or 1.5, depending on how comfortable you are. Okay, so let's say you don't feel quite comfortable because there's so many things, there's so many unknowns in the pipeline. Okay, you don't know how rusty the pipe is internally. Okay, maybe there are some other valves here and there. Maybe there are some pipe reductions here and there that you can't really account for. And then let's say you say that, look, I'll feel safer if, let's say, right, all right, and multiply this Zmax value by 2 and build a search tank that's 10 meter tall instead of building it close to 5.06 meter. Okay, just to be on the safe side. All right, that is a very, very common practice. Actually, part of the safety procedures, actually, you always have got some safety factor. You don't just use the exact numbers when it comes down to engineering. Okay, all right. So, yeah, okay, I think that is the last slide for unsteady flows. Okay, and for search control as well. Okay, I think this is good timing because now it's about 11:26. Okay, so I think it'll be a good time for us to go for a break, and then we come back again in about 10-15 minutes. Yeah. There's a very interesting question. So a student asked for exam, if we use first estimate, will I be giving you the full marks? Well, it depends on the question, right? If the question says, I'll be happy with the first estimate, then by all means, just give the first estimate and stop there, isn't it? Or maybe, exam questions may say, if let's say there's such a question, the exam question I can always permit, I say, look, try out 3 iterations, all right, and show me what's the closest Zmax value you can get. Let's say, I can do that as well, isn't it? Okay, all right. Don't stop giving me ideas, young people. How many iterations you guys want? Okay, stop giving me ideas and then torture yourself instead. Yeah. Okay. All right, young people, go and stretch your legs. I need to stretch my legs as well. All right, I'll come back. Let's come back in about 10 to 15 minutes, and then we'll continue. All right, with the tutorial. Okay, I'm gonna stop recording now. Okay, I'll see you guys back in a jiffy.